You are currently hurtling through time at the speed of light. But be careful. If even a tiny bit of your breakneck temporal velocity leaks into one of the dimensions of space, and you're standing in the wrong place at the time, you will rapidly accelerate to your doom. You think I'm kidding? I just described the true source of gravity. Don't look down. Clocks run slow in gravitational fields. Our GPS satellites tick faster by a factor of 1 in a billion, enough to throw their position accuracy off by 11 kilometers per day. In our recent episode, we saw why this gravitational time dilation is inevitable. It follows as surely as 1 + 1 = 2 if we accept the two axioms of Einstein's relativity theory, that the speed of light is constant for all observers, and that the weight induced by acceleration is fundamentally the same as that induced by gravity, the so-called equivalence principle. But none of this is very satisfying. We know that gravity must cause clocks to run slow on the basis of logical consistency. And we know that gravity does cause clocks to run slow based on many brilliant experiments. But I never explained why or how gravity causes the flow of time to slow down. And I'm not going to explain it now, because in a sense it's not true. Gravity does not warp the flow of time, it's the other way around. The warping of time causes gravity. That's what I'm going to show you right now. If you didn't watch the previous episode, do it, although it's also okay if you watch this one first, just don't forget. So, how is it that time causes gravity? Let's start with a teapot. A nice china teapot hanging in space, minding its own business. Absent a gravitational field or any forces, if the teapot starts motionless, it will stay that way. At least, it stays motionless with respect to the 3 dimensions of space. Everything is moving through the dimension of time. We can show this with our old friend the space-time diagram. Let's have just 2 dimensions of space, so we have space for time. We show progression through time as the object moves up. You could say that it has a positive velocity through time and 0 velocity through space. Okay, now let's add a second object, something nice and massive. The planet Earth will do. We know that the presence of energy and mass warp space-time, and the most intense part of that warping is in time, our gravitational time dilation. Things closer to the Earth move through time more slowly. We can show this as a bunch of identical clocks. They tick as they move up. Clocks closer to the Earth take longer to tick for every tick on a distant clock. Velocity through time increases away from the Earth. If we move particles through time according to those velocities, we have this sense of time flowing in a gradient. Faster streams distant from the Earth, slower streams near it. Kind of like how water in the centre of a stream flows more quickly than at the edge, where the shallower stream bed drags on that flow. It's almost like the Earth's mass creates a drag on the flow of time around it. So, what happens to an object sitting in this stream of time? Parts further away from the Earth age faster, right? Well, yeah, but that's not all. We can think of any object as being made of many tiny clocks, each atom, each subatomic particle trying to tick at its own rate. And each of those clocks has a velocity vector in time. So what's the temporal velocity of the entire object? In Einstein's relativity, you have to remember that time and space are not independent of each other. Objects don't just have a velocity through space or through time, they have a velocity through space-time. We call this their four-velocity. To get at this, let's move away from our teapot for a second and talk about boats. Imagine 2 boats on an actual stream. One near the edge moves slow and one near the centre moves fast. The slow boater reaches out an oar which the fast boater grabs. What happens? Instinct tells us that the fast boat is pulled towards the shore. We can think of the 2 objects as becoming one object, and the difference in velocities across its length causes a torque that rotates the overall velocity vector towards the shore. It's the same with the forward velocity of an object in a gravitational field. The gradient of velocities causes the overall forward velocity of the object to be rotated. All individual forward velocities start out being pointing purely in time, but the sum is rotated partially into space. And it's always rotated in the direction of the decreasing flow, which in a gravitational field is downwards. So, this is the motion of an object in a gravitational field. It gradually picks up velocity in the down direction, it accelerates, and it pays for that acceleration by losing velocity, decelerating in the time direction. There's a certain way of interpreting the math of relativity that says that everything travels at the speed of light. Light travels at the speed of light through space, obviously enough, and we know that nothing with mass can reach that speed travelling through space. But if we interpret time as a dimension like space, then a stationary mass really is moving at the fastest possible speed in the temporal direction. This is something we can come back to another time. For now, let's go with it. The forward velocity of a massive object is pointed almost entirely in the time direction. On the other hand, light itself travels at the speed of light only through space and not at all through time. The photon's clock is frozen. You might imagine its forward velocity is entirely rotated out of the time direction into space, although technically photons and other massless particles don't have a forward velocity, which is defined according to the ticking of their own clock, your proper time, which is 0 for the timeless photon. In this picture, a falling object trades some of its enormous velocity through time to pay for a small velocity through space. To us, the currency exchange looks favourable for space. A teapot gains a rapid plummet to its doom for an imperceptible slowing of its clock. We see the same favourable exchange when we try to convert mass into energy via Einstein's most famous equation, E=mc². The speed of light is the exchange rate, and the speed of light is very large. By the way, two of my favourite physics channels have great, slightly different explanations of this effect. Check out Nick Lucid on Science Asylum and Eugene Kuturyansky's channel to get their takes. So, is that it? Do we now perfectly understand the source of gravity? Well, speak for yourself, I'm still quite confused. This raises thorny questions like, what about a particle with no size, supposedly point-like particles like electrons, quarks, etc.? Well, actually, nothing truly occupies only a single perfectly defined position in space. Quantum uncertainty means that everything is always in multiple places at once, and so experiences a gradient in time flow. But actually, general relativity doesn't need quantum mechanics to explain gravity. It's enough to imagine clocks that are infinitesimally separated, and we still have our time gradient. The other thorny question is about light itself. If photons are already fully rotated into the spatial direction, how is it that they're also affected by gravitational fields? They have no velocity through time to trade. But light does bend in a gravitational field. Astronomers see it happening all the time in the effect we call gravitational lensing. In fact, the imaginary paths of light rays were one of the most important tools that helped Einstein develop both special and general relativity. So we had better understand the effect of gravity on the path of light. To do so, we're going to need to shift our perspective in a couple of mind-bendy ways to see how the flow of time determines the paths of even timeless particles. And with those new perspectives, we'll gain a new insight into the source of gravity that seems weirdly at odds with everything I just told you, and yet is simultaneously exactly as correct. But first, you're going to need some time to think on everything I've just told you and let it settle, and we're going to need some time to make that new episode of Space Time. Last time we talked about the gravitational wave background, that ambient buzz of gravitational waves from the distant and ancient universe, which, by the way, we may have detected using a pulsar timing array. Ivan Kilmock asks where we can find the audio files of the pulsars that we played in that episode. Oh, sorry, I should have linked those in the description to that video, but I'll link them in the description to this video. They are from a number of different radio telescopes, but were collated by the Parkes Observatory in Australia. Stu Laura asks if I can elaborate on my comment, the time before the Big Bang, which I mentioned in reference to a potential source of the gravitational wave background. I was referring to extremely energetic events during the inflationary epoch, fluctuations in the so-called inflaton field, or in the final decay of those inflatons at the end of inflation. I call this before the Big Bang because many physicists are moving away from the picture where you have the Big Bang and then you have an instant of inflation, then regular expansion. For example, in the eternal inflation model, inflation may have lasted for a very, very long time and may still be continuing almost everywhere, but has ceased in isolated bubbles corresponding to the formation of new universes. it makes more sense to talk about the end of inflation as the beginning of such a universe, rather than talking about the beginning of global inflation. So in that case, the last instant of inflation is the instant of the Big Bang, and gravitational waves may travel through that instant from earlier times. King Kusnacht asks whether gravitational waves can be used to test ideas in quantum gravity. Well, the answer is absolutely. The most well-known prospect is by detecting the signatures of primordial gravitational waves, waves from the inflationary epoch. These could be found in the gravitational wave background, but also indirectly through their effect on the cosmic microwave background. Interaction of those waves with matter right after inflation may have caused characteristic patterns in the distribution of matter, which we might now see in the way the CMB light is polarized. The BICEP 2 experiment claimed detection of these so-called B modes, but it turns out they were wrong. But the B modes may be there, and we're digging deeper to find them. During inflation, it's believed that quantum gravitational effects would have been very important, so if we can get any type of gravitational wave signal from back then, perhaps we can learn something. No Mercy 8008 says that the way I described the boats rocking on the ocean as an analogy for gravitational wave detectors suggests that I would be an awesome dungeon master. Well, I'd say I'm at best an okay dungeon master. I think I just rolled a nat 20 on my skill check to describe boats rocking on the ocean. Or did you fumble your saving throw versus being impressed by someone describing boats rocking on the ocean? Anyway, thanks for the compliment, and for reminding me how much I missed the game. So, who wants to play?